At resonance, the tuned circuit becomes the inductive reactance and capacitive reactance will cancel out. So at resonant frequency, the tuned circuit will behave like a pure resistor. Okay, because the reactance part becomes zero. For a resistor, it's a element where voltage and current are in phase. So at resonant frequency, the tuned circuit acts like a resistor where voltage and current are in phase. When I'm going to increase the frequency, see this graph, when I'm going to increase the frequency beyond F naught, the graph falls down. So when the reactance is reducing, it is because of the capacitive effect. For capacitive reactance is given by Xc is equal to 1 by omega C. So as I increase the frequency, my capacitive reactance will decrease. So the proportion above F naught is because of the capacitive reactance of your tuned circuit. So see here, for frequencies above F naught, the circuit act like a capacitor where the current is going to lead the voltage. Okay, in a capacitor, current V and I are out of phase by 90, and current is going to lead my voltage. Now you see the frequency below not the frequency. If I increase the frequency, my reactance is increasing. XL equal to omega L. As I increase my frequency, the inductive reactance will increase proportionately. So the portion below F naught is going to produce an inductive behavior. That is because of the L in your circuit, and the portion above F naught is going to produce a capacitive behavior because of the C inside the circuit. At F naught, it is because of the resistance R. So you have an LCR and you have an LCR in your tuned circuit. Ideally, this R will be zero. Practically, this R will be present because of the wiring nature of your inductor. So you're able to understand how the graph will has three regions which exhibits the behavior from inductor, from capacitor, and from the resistance. Okay. So at frequencies below F naught, as we have seen now, it acts like an inductive one. So the reactance is increasing. So it is because only in inductor the reactance will increase its frequency. So the circuit will exhibit an inductive behavior at frequency less than F naught. And in inductor voltage will lead the current, or I can say current will lag the applied voltage. So whatever the transistor gain you are going to have, it is directly proportional to load impedance. So load impedance means here in the load side we are going to have a tank circuit. So when L and C cancel at the frequency, resonating frequency, only the resistance value will be there that will contribute to your gain of the amplifier. So in tuned circuit, we bother more about the resonant frequency because that is the frequency at which you get maximum gain. And we don't essentially measure bandwidth for a tuned circuit because we know the tuned circuit is going to operate only for a very limited band of frequencies. So we are more bothered about what is F naught. F naught will decide the frequency of operation of the entire circuit. Okay, so this is the inferences whatever we have seen from the frequency response graph of the tuned circuit. So a parallel tuned circuit will have a very high impedance at the frequency of resonance, and the impedance falls off sharply as the frequency depart from the frequency of resonance. So when you compare series and parallel tuned circuit, here we are using a parallel tuned circuit, right? So a parallel tuned circuit will have a very high value of impedance at the frequency of resonance. So at resonance, the value will be pure resistance on either sides. It will be decreasing as you move away from the frequency of resonance. So the gain versus frequency graph is almost similar to the impedance versus frequency graph of the tuned amplifier. What they are saying is if you draw, this is the frequency response of a tuned amplifier. If you draw the impedance of the tuned amplifier, it will be the same as this graph only. So at F naught, you will have a peak resistance. On either side of F naught, the impedance will fall off at a sharper rate. So they are saying generally a parallel tuned circuit will have a huge amount of impedance when you compare to the series circuit. So that is what is the inference. And when you plot the frequency response of the tuned amplifier for parallel circuit, they say that the gain versus frequency response graph is exactly same as the impedance versus frequency response graph. See, it is impedance everywhere except at the resonant frequency, it becomes resistance. Okay, so generally we call it as in y-axis we plot impedance, in x-axis we plot frequency. So when you draw the impedance versus frequency response graph, you will get the same graph as we got here. Okay, so they mean to see that the frequency response graph and the impedance response graph is going to be almost similar for the tuned amplifiers. So tuned amplifiers are therefore only a very narrow band of frequencies you can amplify using a tuned amplifier. So the classification is we have small signal tuned amplifiers and large signal tuned amplifiers.